very pleased to welcome Alex Forrester from the University of Southampton. So I guess I met Alex, when was that we did that thing? Last year, April?
Yeah, in Saint Etienne.
I don't know. We did a thesis fiver together, and Alex is he's using surrogate modeling in engineering design, which I love because I was a mechanical engineer as an undergraduate at Southampton actually, and the thing I didn't like about design is it seemed very no maths. So Alex is bringing the maths into design with surrogate modeling and doing some really interesting projects, which just show with imagination the sort of thing you can do with these models. So he was a perfect choice to kick off this morning's workshop. So over to you, Alex.
Thanks very much. Okay, so although I'm an engineer, I've titled this a little bit as to make it approachable for the kind of people I'm expecting to see here. It's sequential sampling for robust design. So an engineer wouldn't know what you mean by sequential sampling. What I mean by that is sampling is running some experiments or doing some computations, and each one of those experiments or computations gives you an answer back that's a sample of your design space that you're trying to search. And you do these experiments or computations one after another or in batches in a sequence, and you want to get to the best answer as quickly as you possibly can. So that's what I mean by sequential sampling. For robust design, people always want the optimal design, but this is an optimal design when there's some uncertainty in the conditions or the manufacture of your product. And it's a reasonably new area because everybody got very excited about using surrogate modeling for deterministic design when there isn't any uncertainty. And there's been a lot of work there, and people have just ignored the fact that there's so much variation in engineering components and engineering and the operating environments of them, and people are now getting on board with robust design. So I'm going to start off with a really quick look at the basics of using what I've up until now been calling surrogate models, because I like the idea that it's a statistical mathematical model that you use in lieu of a true analysis or true experiment. So it's a surrogate for those experiments. But people also call them response surfaces. That's perhaps more often used for polynomial models or meta models, also emulators. But you have to be careful when you call it an emulator. Especially in Sheffield, Tony O'Hagan I think gets upset if you call the wrong thing an emulator for the wrong reasons. But anyway, I'm then going to go on about how you go on to tell you about how you use these surrogates for optimizing functions, and then go on to finally look at dealing with noisy data or when there's uncertainty in your answers, and then have a look at how we can use go on to do optimization with robust design. Okay, so just a quick recap so we're all on the same page as to what we mean by optimization. In optimization, you have some kind of controllable variables, things that you can change, that will affect some outputs, and you want to make these outputs as good as possible. And you'll have some kind of way of getting to these outputs from these controllable variables, whether that's some sort of computer model or whether it's actually going through the process in real life. And there'll be some other environmental variables that are going to impact on this. And if you change your controllable variables and look at the outputs and then make a decision based on what happened with those outputs, and you go round and round this loop, you can hopefully get to an optimal scenario. And depending on the audience, a scenario I sometimes use is you could imagine that the output here was your kids getting to sleep on time, and the controllable variables were things like, when you actually finally told them to go to bed, what you fed them for dinner, how long you read to them, and the environmental variables would be, maybe they had cake at school, what was the weather like, what was the traffic like, and so on and so forth. And if you ran this experiment night after night, the environmental variables, everything will get swallowed up in those, and you perhaps never really get to an answer. But if you were really methodical about it and got your spreadsheets out and put in exactly what you did with the kids every night and built some kind of statistical model of the effect of these things, you could maybe get there a little bit quicker. So when I'm trying to get my kids to bed, what I would do is I would have built a statistical model of the scenario of getting the kids to bed, and then I'd be able to try out different controllable variables and environmental variables and hopefully get there as quick as possible. And so this is the idea of a surrogate model, that instead of actually running the real analysis, to actually make it a bit more approachable, say it was an aircraft, and instead of building 1,000 aircraft, you actually looked at the performance of a handful of them and put some kind of curve fit through them. That would be a surrogate model. Okay, so we're going to use surrogate models to do optimization by putting them in the middle of this loop of controllable variables, figuring out what's going to happen, and making decisions. So what we need to do to build a surrogate model is we need to run a load of experiments to begin with. So rather than actually having the physics present in the model, we're going to use some statistics. It could be a polynomial model, it could be a Gaussian process model. This is an example of a function that's often used to demonstrate the performance of surrogate models. So this is one of our controllable variables here, this is another one, and this is the response that we get for the different values of these controllable variables, and these are the minima of this problem. So if it takes a day to calculate one value off here, we're not going to just run an optimizer on this because we'll be there forever. Instead, we've where these black dots are, we've run 20 simulations, and we actually get that as our surrogate model using a Gaussian process method, popularly known as Kriging. And it looks really, really similar. So Kriging, you might as well use that based on 20 evaluations rather than resort to the true function, which could take you days to calculate. Imagine if you had to crash a car to work out the characteristics of the crashworthiness of that car every time. You'd be better off crashing 20 cars and building that than resorting to running your optimizer on this. So that's the basics of surrogate modeling. Now, sometimes your function that you're trying to minimize is a little bit complicated. This is an example of a toy function where this is our variable here that we're changing, and this is the value that we're trying to minimize, and this dark line here is the true function. So ideally we'd want to find that point there. Now, if we take a pragmatic sample to begin with, and we have a point here, here, and here, that's what our initial surrogate model looks like. So it's deceiving us somewhat, and it looks as though actually the optimum's over there. In one dimension, this is obvious. You would think, well, I don't want to put all of my effort over there because maybe I want to have a look there as well. But let's say this is a 10-dimensional problem. You wouldn't be able to make these sorts of decisions using your human mind. You'd have to rely on the computer. So what we do is we say, well, let's try another experiment at the minimum point, and we'll refit the model. And then we'll try another experiment at the minimum point, and we'll refit the model to try and enhance the accuracy of the model in the area of optimal solutions. So you do that with this model, and you just end up stepping down towards this local minimum here. So it fails miserably. If you just fit a surrogate model and then make sequential updates at the minimum, it seems like a wonderful strategy, but you've just got quite an efficient local optimizer. So if your initial sample doesn't capture all of the humps and bumps and everything in the function, you're going to fail. Now, what we need to remember is if we're fitting a Gaussian process model is that it's just the mean of many different possibilities of that forms that function could take. So this is our previous failed optimization, and we base that optimization on this dashed line here, which is the mean of all these possibilities. So what we've done is we've said, well, we think the function is going to be smooth, and then we've conditioned this posterior here on these data, but we do know that there is this probability that the function could take another value. All we've shown in the previous plot is the mean, and that's not the true story. So based on the variance in our prediction, which I plotted here, so it goes to 0 at all the places where we previously sampled, but it's high in the gaps because we've got this spread of potential functions here. We can do some more interesting things. So we can calculate things like the probability of improvement. So for example here, the probability of improvement in this situation is if we take the distribution of potential answers at this point here, we can integrate the area of that below the best point so far, and that will give us the probability of improvement. So instead of saying, well, I always want to put in a new design at my predicted best point, you say, well, I would like to put in a new design where the probability of improvement is highest. And instead of the probability of improvement, you can also calculate things like the expected improvement. This is what you get from the expected improvement, and it's got this big peak here, so it says that's where you need to go. And this makes intuitive sense. Okay, so what about when there's uncertainty? In those previous plots, we've had a true function, and it's every time we run it, it's going to give us the same answer back, which is not the situation when you put your kids to bed, and it's not the situation when you build an aircraft engine. So this is an example of a function where we're trying to minimize the drag here of aerofoils that vary in shape as we change this parameter. And I've got 101 computational fluid dynamics simulations here, and they're really quite noisy, just because it's we're not solving the true problem. We're solving something that's discretized over a mesh that we're using to get a solution to some inviscid computational fluid dynamics equations. So this is an example of some noise you might get in a problem. It's not the same sort of noise as you would get in the real world, because it is actually repeatable, so it's what we've called deterministic noise. Every time you run the same simulation, you would get the same answer. But if you run a simulation immediately next to a previous one, you'll get a different answer. So it's a kind of noise. So this is another advantage to using surrogate models, because if you're using something like a gradient descent method, or you will naturally take it will take you a long time, because you'll need quite a few simulations to get to an optimum design, and also you can't calculate gradients here very easily. If you've got an adjoint solver, you can, but if you're just trying to do finite differencing based on a couple of computational fluid dynamics simulations, the gradients are going to be wildly inaccurate. So if we fit a smooth line through these data, a smooth surrogate model, your optimizer will then get on better with it. Okay, if we don't do that, if we just use an interpolating surrogate model, one that goes through every single point, we'll have real problems when we run something like an expected improvement update strategy. So what we've got, it's a little bit small, is we've got 4 initial simulations here, and we look at the expected improvement, and it says, well, sort of either side of those simulations there are where we're likely to get the most improvement. So we put a new simulation in here, then we look at the expected improvement, and it's come up on this side there. We put in a new simulation, and we're gradually getting towards the optimum. But then everything becomes a bit snaky, because we've got this noise in the data, and we've got this, we end up with this very wiggly surrogate model. So the expected improvement actually starts to get bigger and goes off in all different directions of the design space. Now this is a really simple function, it just does that. And we can see what's going on here, but imagine if we were, again, in 10 dimensions, you wouldn't be able to visualize this, and you'd think, oh, I've not found the region of the global optimum there, I need to keep searching, and it would go on forever. So we need a way of dealing with these the noise in the data. Here's the original model that we put through here. So the solution is some kind of regressing surrogate that smooths out the noise in the data. So you can see how we were going to start to struggle with this dashed line one. Is the optimum here? You know, we're putting another point there. It's probably going to end up being over here. It's all over the place. But if we optimize the smooth dark line, we're going to get to the optimum of this problem. it's going to be the optimum on average because we've got this noise about the function, but that's what we're most interested in this scenario, you know, the optimum of this mean fit. That's what we're interested in for the moment. So we put this smooth regressing surrogate model through, and the problem is we then need to calculate the error in this model so that we can then calculate the expected improvement. So if I flick back just a few slides, we need to have a look at what this uncertainty is so that we can then look at things like probability of improvement and expected improvement. The issue is that while before our error dropped to 0 at previously sampled locations, if we include a sort of fudge factor constant in the correlation matrix that our Gaussian process model is built from, we end up with error that doesn't go to 0. So if we look at the error in this model here, it actually looks like this. It never goes to 0. It gets sort of low where we've sampled previously, but it doesn't actually go to 0. So our expected improvement search doesn't really work very well. If we start at the same place as before, we've got a high expected improvement there. We add in another point, and we've got a high expected improvement here, almost the same place. After 2 updates, our expected improvement doesn't actually change at all. So we've not found the actual optimum here, but the any possible variations the function might have in that region have been masked by the noise that we've got in the data, and the optimization is basically stalled. If this was a slightly more complicated design space, we'd never find the global optimum because we're too busy trying to put in repeated simulations to bring the error down when the error will never come down. Now, that means that what we want to do is make the error go back to 0 at places where we previously sampled, because we don't want to go back there again. Now, there's a few ways of looking at this. For the moment, what we'll say is that we're not going to get any more information if we run an experiment twice, and that's what we would want to do if we're running computer simulations. It's a bit different if you wanted to do if you were running physical experiments, when you may well get a different answer the next time, so you might want to run an experiment again. But we'll get onto that in a moment. For the time being, we would like our error in our surrogate model to be 0 at a previously sampled location, so that we don't risk going back there, and we can have a nice global search of our problem, but without the excessive snaking that we got when we were using an interpolating model. So what we actually do is, if we go back to this function here, we calculate our error as if these simulations actually lay on the regression line. So I call this reinterpolation. This is what would happen if we had an interpolating model through the noisy data. Instead, we put the regressing model through, but then if we refit an interpolating model through the regressed data, we'll get a smooth model, but our error will return to 0 at all the sampling points, and our optimization can go on as standard. You could do it that way. You could fit multiple models, but actually the maths works out so that all you need to do is make a change to the variance in your Gaussian process model. I'm leaving the maths in there because this relates to papers on this, and you could look at this later if you wanted to, but I don't think anybody, well, I glaze over when I see things like that in presentations. So we'll concentrate on the morals rather than the equations, but it's a simple fix to the variance in your Gaussian process model. So what happens now is, if we calculate the expected improvement, if we calculate the error, it looks like this. We've got near 0 error where we'd sampled before, and we get a big error where we hadn't. So that plot looks a lot more reasonable than that one, taking into account where we'd got these experiments. Okay, so now our expected improvement-based search is global again. We've got these 2 peaks either side here to begin with. Then it all looks a little bit like the interpolating one to start with. We really start to narrow down on this optimum here, and once we've explored that area, we start to get these expected improvements over here. But now the actual value of our expectation of improving in the drag here is 10 to the minus 40 something. It's very, very low, so we've got a good indicator that we've actually finished our optimization. Whereas before, with the interpolating model, we had very high expected improvements, making you think, oh, well, maybe we need to keep on the search. And in all these scenarios, you need to think, well, what if this was in 10, 20 dimensions? All I've got to go on is the numbers, really. So this is very nice. But what happens if we've got real noise? So in these previous examples, we've said that we've got this really wavy function, but if we run a simulation again, we'll get the same answer again. What we actually want to think about is, let's say we're building an engine. If we run one engine with one set of manufactured turbine blades in, and we run another engine with another set of manufactured turbine blades in, we'll get a different answer because of the manufacturing defects and so on in these blades. You need to take into account this uncertainty, and that's what robust design is all about, making it so that you've not necessarily got the best possible performance that an engine could give you. You want your whole fleet to have the best performance. So we need to take into account that when we run an analysis again, or we run an experiment again, we'll get different answers, and we need to find the area in our design search space that gives us the best answer on average. So, has David turned up yet? Not sure. Right, okay, so in Bern, David Ginsberger and Victor Picheny came up with this idea called expected quantile improvement. I think they've kind of moved on a little bit since then, but I've still been playing with this idea because I think it's a good one, especially if you couple it with some of the stuff that we looked at earlier. Now, so far we've been minimizing the mean of our Gaussian process model. So what we actually want to do is have a look at what's the a worst possible scenario. So instead of looking at the not worst possible, one standard deviation, two standard deviations, or whatever above the mean. So instead of minimizing the mean, we minimize a quantile. So this quantile here is the mean of our Gaussian process model plus some beta quantile. So what we end up with is, go to this one to begin with. This is the mean of our function here that we've got, that we've estimated based on these 4 sample points. This is the actual data from the function we're minimizing. It's the same toy function as before, but you can see the dots here everywhere. This is a noisy function. Based on these 4 data points here, as well as this mean, we've got an upper quantile. So the quantile dips a bit at each sample location because we've got a bit more confidence there, and in between it goes up where we've got less confidence in our model. So what we want to do is try and minimize that. And if we see, you have a look here, that the data's all very close together here. This function is nearly deterministic at that point, and as this variable changes, the spread of data gets worse. So our uncertainty increases as we move along the function. So it's not clear whether we want to be here, where there's less noise, but it's got quite a low value, or if we want to be over here, where there's lots of noise, but it looks as though on average the value is lower. So what we can do is with this this quantile improvement is we've got 2 controllable parameters. We've got the beta here, which is our confidence that's going to determine how far above the mean we want to be. And if we had it at if we have a low value of beta, we'll head more towards this mean function. If we have a high value of beta, we'll go up more. And then we've also got this noise parameter here. And if we've got very low noise in our observations, we're going to be more towards the mean. This is with tau squared equals 0. And as we go up in values of tau squared, we increase here. Okay, so basically all we need to take home from this is that instead of minimizing the mean of the function, we're going to minimize some sort of upper quantile, which makes sense because you're saying I don't just want one single engine that sits at the middle of my data set to be performing well. I want them all to be below a certain limit of performance, or I want 95% of them. So this method that Piccinini developed was developed for experiments with tunable precision, because a lot of people work on, let's say that instead of actually the inherent defects in our artifact, we were looking at measurements in our artifact. So if I take my calipers and I measure it, if I have if I take one measurement, I'm not going to be very certain as to the dimensions of this part. If I take 10,000 measurements, I'm going to have a really good idea of the size of that part. And Piccinini developed this for those sorts of situations where the more measurements you put in, the more this quantile is going to drop. So by adding more measurements or more experiments at a certain point, you're going to start to bring down this quantile. Another way of looking at it is, say it was an iterative solver, some kind of computational fluid dynamics. At early stages, you've got a very rough idea. As you iterate the solver to convergence, you've got a more accurate idea. Or Monte Carlo simulations. Where do you want to focus? More Monte Carlo simulations to bring down this quantile. The thing is, for robust design, you've got irreducible noise. The noise is there. You're going to build these engines, and the parts have got this defect in that's set in your manufacturing process, and you want to feed in the controllable parameters that are going to mean this noise, the manufacturing defects are going to have less effect. By running more simulations, you're not going to make the engine part any more accurate. So you've got this irreducible noise that you actually want to quantify. So instead of using this this quantile here, where you can choose this tau squared based on how many iterations of your Monte Carlo solver you're going to have, for example, we're going to base the error here, the quantile here, on the error in our Kriging or Gaussian process model. So if we, but the noise varies throughout the search space. So as standard, this parameter here of the noise in your Kriging model would be based on a single value that you've added to your correlation matrix, this regression fudge factor, which said that you've got your curve fit is going to pass near to your data in the same way throughout your search space. So what we see here is the difference here between the quantile and the error in that quantile is exactly the same there as it is here, because we've assumed that the level of noise is the same throughout, and that's commonplace in almost all regressing type models you'll see. If it's a polynomial model or if it's a Gaussian process model, you normally have just this constant regression term that's added. Actually, what we would like to see is this error reduced to 0 here, because we haven't got any noise in our data there, and it to gradually get wider to the end here, because this is where we've got much more error. Actually, what we've done is we've contrived this problem here, so the standard deviation in our data is 9x squared. So we've got this gradual spread of data as we move through. Okay, so if we run the expected quantile improvement method with known uncertainty, I've actually plugged in that this is actually what the uncertainty is. We can see how it starts to work. It's this dark line here that's the quantile that's lying just above the boulder line below, and we're trying to minimize that, and our error in it is represented by the dashed lines. So to begin with, we have this high expected quantile improvement here. So the quantile's quite low and we've got error in it. And we gradually work our way through. At a point here, here's the improvement. At a point there, there's the improvement, and so on and so forth. And the problem is, it's just getting stuck here. we know this is where the optima are, over here and over there. So it's far too conservative. It's not. It's exploiting the initial model. It's not actually exploring enough. So the problem that we've got here is we want to minimize a quantile that sits a certain amount above the mean because of the inherent underlying uncertainty in our data. So that's this uncertainty here. But we want to explore that model because of the uncertainty we've got in our prediction of that quantile. So what we've got is we've got two sources of error there. We've got the error in the data that we can't get rid of, and we've got the error in our prediction of the quantile, the error in the emulator, which we can reduce by adding more data. So if we throw in thousands of simulations, we can get a really accurate prediction of the upper quantile of our problem. We can never reduce the error that's inherent in the manufacturing process, because at this time we're designing with that being an immovable error in our process. So what we need to do is we need to decouple these errors. So we're searching for the minimum of this upper quantile, and we're searching based on a trade-off of how low that is and what our error is in estimating the quantile, not the actual inherent error in the data. So what we need to do is go back and do the same thing as we did with when we reinterpolated the regressing model at the beginning, when we're talking about deterministic data. So what we do is we get this regressing model here, so it's the quantile, and refit a smooth version of that so that we can then remove the error due to the noise in the data and only look at the error due to the noise in the only look at the error due to us not having enough sampling. So we end up just here. We've got a high error where we've previously sampled. So we might end up going back to these points. Now, this is where we get to the slightly controversial notion of, do we want to resample at a previous location? Now, lots of people, I think you'll find lots of people who would say you should use Latin hypercube sampling because it gives you even projections onto each of your variables. You don't want to have a full factorial design because you'll have all these lined up experiments and it's a waste of time. So we should have stratified sampling, Latin hypercube. That's a good way to go. And then the same person would say to you, oh, well, if you've got uncertainty, you need to do some repeated experiments at a point so that you can figure out what your variance is for that design. Now, those two arguments don't really tie up with each other because if you imagine your uncertainty as another dimension of your design space, you should try and have this sort of stratified sampling across the whole thing. Now, if running a repeated experiment, you take 10 hours to set up the experiment and then you just press a button 5 times, I can understand that a repeated experiment might be a good idea. But if you have to make a whole new artifact every time you run a new experiment, it doesn't make sense to run the same experiment twice. That would be the same as using a full factorial design, for example, where you don't want to repeat experiments at the same parameter values. So this is the premise by which I say that we don't really want to sample at this location again, because it's not going to tell us as much about our design space as sampling somewhere else. And by sampling somewhere else nearby, we'll also get an idea of the noise. So, back to where we were. We would like the error at these points here to diminish to 0 because we've already evaluated our model there, so we're not going to learn sufficiently more about the location of our quantile as we are if we sample somewhere else. So let's have a look at this at what happens here. This is our quantile, estimates of our quantile, this dark line there, and these dashed lines are the error in our quantile. So it's the same as almost the same figure where I showed you all the different possible Gaussian processes, and we take the mean Gaussian process, and then we have we estimate an error. What we've got here is the same scenario, but we're looking at a quantile. The quantile still sits above our mean model because of the inherent uncertainty in these data, but our error in estimating that quantile diminishes to 0 at each previously sampled point. So we run this optimization, and this is the same optimization as here. We're trying to solve the same problem, but we've done this reinterpolation thing so that our error diminishes to 0 at previously sampled points, and we get a much nicer global search. It starts the same as before, with us wanting to sample in the middle because the quantile looks pretty low there, the error is quite high. But as soon as we put data there, it starts to indicate that we want to go somewhere else. A couple of experiments there, then it finally takes us over to this region here. You can see we've got an high expected improvement there. So we've managed to get a global search of this problem that's got uncertainty in the data, and we're trying to minimize a quantile. So what we've taken is the efficient deterministic optimization that we had at the start, and we've put it in the context of robust design, and we transferred across almost all of the benefits of that first method, which has been used in deterministic design for a while. It works really nicely. The thing is, of course it works because I've actually plugged in there the value of the uncertainty, and this is an uncertainty quantification workshop, I think that's what it's called, isn't it? And I've just said, oh, well, it's 9x squared. So what we need to do is actually estimate the uncertainty, and that's a little bit more tricky. Okay, so as I said before, usually regressing emulators use a constant regression term, and you have a correlation matrix of all your data correlated with itself, and down the diagonal you have ones, and if you're doing regression you just add a bit to that, and that makes it so that your model doesn't pass through the data, it goes near it. We don't want to have this constant regression term because we've shown that your uncertainty may vary throughout your search space, and we want to be able to quantify that so that we can do these nice searches like this. But we want to estimate the uncertainty rather than just plug it in. So what we do is we assume that the uncertainty is a function of x. What we could do is, the slow way to do it would be to choose a load of points throughout the search space and run hundreds of experiments at each point, and then we get a variance at each of those designs, and then we'd use that to estimate it. But we want to have this more stratified sampling. So we assume that noise is a function of x, and what we're going to do is we're going to find a whole load of values for our regression term to fit in along the diagonal of our correlation matrix. So every sample point has a different regression term associated with it. So we're going to have a two-stage process. We're going to fit a standard regressing model that has a constant regression term in it, and then we're actually going to build a Gaussian process model of the regression parameter as a function of x. And starting from this constant regression, so it smooths the data in the same way throughout the design space, we're going to run a gradient-based search that's just going to tweak it to try and make the model fit the data better based on a non-stationary regression term. So this is an example of trying to figure out what the regression term should be for this same problem, and I've got a whole load of data in here actually to begin with, and if I use a constant regression term I get this mean fit here, and this is my error around it. So it stays constant the whole way because I've got this constant regression term. Now, what I do is then, at a few discrete points throughout the space, start at these points with the same regression constant at these points, and then fit a model to these regression terms. So that will be a flat line to begin with, and then based on maximizing the likelihood in these data here, tweak the values of these regression terms, and it ends up giving us something that looks like this. It should equal 9x squared. It doesn't quite equal, or it should be a function associated with 9x squared, so it should go up like that. We've got an anomaly here, because things get a bit difficult to fit up at that end, and I haven't actually got a data point there. But in general, I've managed to get the basic gist of how the noise increases as we move from one end to the other end of this data set. And then when we recalculate the errors, rebuild the model based on a different regression constant for every point, we get something that looks like this. And our errors are down at 0 at that end, and they gradually grow. So I've now managed to estimate this 9x squared variance based on a gradient search of a non-stationary regression parameter, and we can now go ahead and use this in optimization. And it doesn't look exactly the same, but we've run the process here using this way of estimating the non-stationary regression term instead of just knowing what it is, and we get the same form of global search where we're actually highlighting these areas of low quantile because we've got a low function value but a reasonably high uncertainty, and over here where we've got a slightly higher function value but a very low uncertainty. So we've got a template for a method that works. I'm currently trying this on some more difficult problems, some structural dynamics problems where the uncertainty has a very high impact on the outcome. Okay, so in summary, Gaussian process is good. For robust design, you can use the power of the GP to create quantiles, and you can use that for robust design. Just the same way as expected improvements being so successful, this expected quantile improvement can be used as well, I think. A real key thing is not mixing up your uncertainties. You've got reducible error in your surrogate that you're fitting, and you've got this irreducible error that's the uncertainty that you're trying to quantify. And if you just apply these methods as they come out of the box, you're going to have this double accounting of errors that doesn't make sense. So you need to try and decouple these. Lots of repeated experiments, Monte Carlo simulations and so on, slow everything down. So I'm sort of an advocate for not doing that, and we'd be better off us estimating the uncertainty as a function of x and having a bigger spread of experiments. If you want to look into this a bit more, we've got a couple of key references from Victor and David there, and Tobias Wagner has done some work here, and then a few of the references that the earlier stuff that I presented is based on. And you can also go to I'm not a very savvy, but I did buy optimization.codes, which I thought was a good move. So you could go there to get some of the code that's used to produce these models. Okay, done. Yes?
You showed the training of this extra model to estimate the uncertainties using a rather large amount of data.
Yeah.
How do you expect this to work when you're starting with like 3 points of data in your model?
Well, that's what's happened here. In this one, I've only got these few points. So to begin with, it doesn't. But the whole idea of this sequential sampling is you only put points where you need the points. So if I put a whole load of effort into calculating the uncertainty there, that would be wasted. So once you get an interesting point from the point of view of the mean being low and the quantile being low, you add a point in there, and then your estimate of the uncertainty at that point just gets a bit better. And you've got this dual process of exploration and improving your estimates as you move through. And what's nice about it is that you using this, if it's in this expected improvement framework, it is a global search. So you may get a bit bogged down in an area where you underestimated the uncertainty to begin with, but then it will move on. And I think that the machinery and the mathematics behind this way of doing it is better than just saying with a broad brush, oh, we'll just try and get a good idea of the uncertainty everywhere.
Have you
Yep.
Right, fitting any heteroscedastic Gaussian process models rather than doing like a post-estimation?
No, I haven't. No, I say I think a lot of my talks are a little bit bit lacking in taking things to that next level, because all of my research comes from the point of view of finding the problem in engineering, and then as a bit of a charlatan at mathematics, having a good stab at it, putting it out in the literature, and then letting everyone else have a go. Okay.
What about excuse me? What about extending to higher dimensions? So, for example, I agree with you. If you have a suitably strong model which allows you to learn appropriately, then doing repetitions is of course inefficient. Okay? However, in higher dimensions, you may have to put a lot of points down to start learning about things in high dimensions, right? If you're learning about variance as well as the mean structure. And then you can run into computational issues in terms of your Gaussian process requires you to invert a matrix, which gets bigger and bigger and bigger and bigger. So do you think this would scale up to higher dimensions?
I think so, because certainly in terms of the this estimating the uncertainty, because you start with a simple model, and then it's a gradient descent search of parameters to complete that estimation. And now we're using adjoints of likelihoods for all of these things. You're not having to do so many inversions. 15 years ago, people were like, oh, you can't use Gaussian processes in more than 10 dimensions, and now we all are. And I think that the efficiency with which you can do these likelihood maximizations has improved to that point. But also, you could take the view in the other sense that if you're in high dimensions, your repeated experiments at various points are just like atoms in the universe anyway. You're going to get more coverage of the design space doing this.
It always depends how smooth you think your surface is versus how difficult the noise is. So, for example, if you think your surface is linear, then you definitely don't want to do lots of points everywhere. You just do d+1 points, and that will nail it, and you do as many repetitions as you want. If you think the surface is wavy, then you need to spread things around as well. There's more of a balance between what you think is the complexity of your variance versus the complexity of your mean.
So I mean, I've got a higher dimension problem that I'm working on, but this is a hobby. Okay, good.